Howdy students, this is going to be the last part of Unit 16, Part 3, and we're going to look at batteries, and we're going to look at the flow of electrons from one side of an electrode to another. So last part of this unit, we're going to look at how batteries are constructed and how they work. And it's not going to look like a normal battery, but this is where we got the basic idea of electricity from. So with batteries, you have two what we call half cells. So we're going to learn about those today. Electrochemical cells that convert chemical energy into electrical energy are called voltaic cells. And of course, you get the word volt from that. And voltage is something that is used in electricity to measure current. The energy is produced by what we call a spontaneous redox reaction. So this is not something that we would have to input energy into. When we have the proper chemicals, they happen on their own, spontaneously. Voltaic cells can be separated into two half cells, and you'll see that on the picture here. This would be considered a half cell, and this would be considered a half cell. And together, they make up the full voltaic cell. A half cell consists of a metal rod or a strip of a metal immersed in a solution of its own ions. So we have copper metal here, and what we're going to have are copper ions floating around in solution. And then on the other side, you have zinc metal, and then you're going to have zinc ions floating around in solution. We're going to write half reactions to show what happens in each part of the cell. When we write the half reactions, we're going to see which species is oxidized and which one is reduced. So here are what we call our half reactions. You would have one half reaction in each of the half cells, and together they make up the full reaction. So in this case, iron goes from an oxidation state of 0 to an oxidation state of 2+. And then here, nickel goes from 2+ to 0, so it is reduced. So in your notes, there's a diagram of the voltaic cell for the reaction of zinc and copper. So we're going to label that diagram. Here are our half reactions. Zinc goes from 0 to 2+. Copper goes from 2+ to 0, so it is reduced. And you'll see that 2 electrons are both a part of these reactions. So we're going to label the zinc strip as the anode, and on the next slide I'll have a little memory device for you to help memorize these. We have two different types of electrodes here. The anode is for the zinc, which is what is oxidized. And then the copper strip is going to be the cathode, which is the species that gets reduced. We have a salt bridge that connects the two half cells together. Without a connection, we have no flow of electricity. We have our metal strips down in here. And of course, we have our solutions that contain ions. And then you have to have a wire that actually is attached to the two metals. And if you wanted to measure the actual current, you could get a voltmeter. And specifically in these solutions, because zinc is over here, we're going to have a solution of zinc ions. And because copper is over here, we will have a solution of copper ions. So the direction of the electron flow is always from the anode to the cathode. From the anode to the cathode. So if I was labeling the directionality, it would be moving from the anode in the direction of the cathode. Now, I could continue it. It would be moving up the salt bridge and then back through here. And this is our flow of electrons. So predict what will happen if an iron nail is dipped into a solution of copper sulfate. Write the balanced equation and the two half reactions. Well, first thing we need to know is that iron is above copper on the activity series. So the reaction actually does occur, and iron is oxidized. So Fe is dipped into a solution of copper sulfate. We're going to have to write a balanced equation for this. Here it is. We're going to have to label our oxidation numbers. And what we're going to see is that iron goes from a 0 to a 2 plus when we label oxidation numbers, and then copper is going to go from a 2 plus to a 0. So iron is being oxidized and copper is being reduced. These are the half reactions, and then there's actually a chart on the back of your notes where we can actually find these two half reactions. And with that, there's actually a voltage attached to it, and we can calculate the voltage on this reaction. So the half cells are connected by a salt bridge. The salt bridge itself is a tube that contains a solution of ions. Ions pass through it, and it keeps the charges balanced, so it continues the flow of electricity. The electrons pass through an external wire that connects both of the metals together. The metal rods are called electrodes. And we have two. We have the anode and the cathode. So oxidation always occurs at the anode, and reduction always occurs at the cathode. So we can use this to help us remember. An ox and red cat. So oxidation occurs at the anode, and reduction occurs at the cathode. The direction of electron flow is from the anode to the cathode, which we say fat cat. From the anode to the cathode. When we have our half reactions, we can take the potential charge and we can add them up from our reduction potential table. But there's one thing that we'll need to know when we're using this table. So we're going to have to write the oxidation and reduction half reactions. But what we're given is a standard reduction table. And so when we're using the oxidation, we're going to have to flip those values from a positive to a negative or vice versa. So here it is. We'll have to flip that sign for the one that is oxidation. Now, they do have oxidation tables. And if this was an oxidation table, then you would be good. But the table in our notes is a reduction table. And then you just add the potentials together. So here's our example. Battery is made with nickel and cadmium. What is the cell potential of this battery? Well, they give us from our reduction tables the voltage for both of these half reactions. So here are the half reactions from the table. And you'll notice that we took the one that was oxidized and we flipped the sign, which allows us to add correctly and get the proper voltage, which in this case is 0.15 electron volts is what we say. So this is what the table looks like in your notes, and just remember that all of these are for reduction processes.